Okay, so welcome back to part 5, where we're going to go through applying those practical skills that we've learned in a mock practice physics exam. Mock physics practice exam, sorry. So, generate a hypothesis. A hypothesis should be, again, as an if-then statement, right? So, we're going to say if the angle increases, so to be very specific, right? Don't just say if the increases from what to what, from 0 to 45, then the range should increase. Then the range should increase. So that's how I use an if-then statement here. If something happens, then something happens. And I've been very specific. As angle increases from what to what, the range should increase. Part B, determine the independent and dependent variables. Independent variable is going to be the angle, because that's the one that we change, right? Dependent, this is going to be our range, right? Because that's the one that we measure, right? So dependent is the one that we measure, independent is the one that we change. So there's quite a few things that we should control, like we should control the Nerf gun used, like the model, right? Like the model, we should use this use the same setting, the same force setting. We want to use the same bullet. We want to make sure that there's no wind. We want to probably do it indoors. Probably also want to use the same protractor. There's plenty of things that we could use. Fill in the table. Now this table hasn't filled already because I have Excel. So boom. Plot the data. Okay. So how do we want to? So how do we linearize the data? So we know that we're given this equation, right? We are given the equation. We're given the equation. This one. So what we can see here is that the range is not directly proportional to theta. It's not, but it is directly proportional to sine of 2 theta, right? This is true. So what I'm going to do is I'm going to grab this table. I'm going to turn the angle of projection into sine of the angle, sine 2 times this. It's going to be sine 2 times, say, 5, if I'm doing if that one, and I'll plot that on the bottom axis, and I'll plot the other one on the vertical axis. Now to save you the pain of me plotting slowly, I am going to speed this part up. Okay, so I've plotted the graph. And I've linearized it by basically having the angle here, and then sine 2 theta in the column next to it. Be like 5, 10, 15, and then you'd have like 0.17, 0.34, 0.5 in a column, and then you chuck it onto the bottom, and we have this thing, and now we are going to insert a line of best fit. Now some teachers will, that was very straight, wow. Now some teachers will insist that you have to go through the most number of points, and you have to have like an equal number of crosses on each side. You have 1, 2 on one side, 3 on the other side, that's fine. Some teachers will, there's quite a few teachers that insist that you have the same number of crosses on each side. That's not theoretically true, but if they say it's true, then it's true. Okay. So using the line of best fit, determine the launch velocity, right? So what is the line of best fit? I can see, oh, hang on, ooh. Very straight line, I'm proud of it. The only problem is that my line of best fit should not extend beyond 1. So let me contract it a bit back to 1. There we go. Perfect. So it seems to go through these 2 points, the last and the first point. So let's calculate the gradient, right? Gradient is equal to change in y over change in x. Rise and run. So let me grab my data. That's going to be 108.24 minus 18.99. So again, I plotted the averages, by the way. So I plotted the averages, and by difference in x, so that'd be 1 minus 0.7. So that gives us a gradient of 107.9. So if we rearrange the formula, we have r is equal to u squared sine 2 theta on g. So therefore u squared is equal to g r on sine theta, right? Sine 2 theta. Now, what have we found? Well, we found so our gradient is equal to sine. So yeah, our gradient is equal to the range on sine 2 theta. So just shove it in, and we get u squared is equal to 9.8 times 107.9. So u is equal to 32.5 meters per second. Okay, let's go on to assessing the accuracy, the reliability, and the validity. Let's assess the accuracy. So we can see that I'll say that it was accurate because the readings had 2 decimal places, which indicates it is accurate. I mean, not really, but it's just a very commonly accepted answer by teachers. Again, it indicates it's precise, not accurate, technically. What else can we say about accuracy? Well, we can say that maybe the protractor was not accurate. So, however, the value of the angle of the gun. We can't really compare it to the true value in this case because we haven't been given one. We can say though that we had that the readings were taken square on, so hence no parallax error. Like when you're reading the angle, you want to read it square on so that there's no parallax error. Okay, assess the reliability, right? So assess the reliability. We can say this is a relatively unreliable experiment. And this is because although it was repeated and averaged, so we can say it was repeated and averaged, which reduces random error by cancelling out. So it was repeated and averaged to reduce the effect of random errors. However, the data variation is huge, right? The data variation is very large in the data set. And you can give an example, this can be seen in the, let's just pick an example here. Let's say at 45 degrees, right? Trial where the range of scores, the range of ranges is going to be from 132 minus 187, so that's 45. It's like a 50% deviation, right? Scores is 45 meters, or 50% of the lowest score. You could calculate standard deviation if you liked with the calculator during the exam. So this large deviation, this large variation indicates that the experimental data has a lot of random error and needs to be performed to really average it out to. You can also say, actually no, I think that's probably enough for our 3 marks. Assess the validity. We can say that it's a relatively valid experiment. Only one variable was changed at a time, and all other were controlled. And he gives some examples like this. For example, the gun, bullet, and force setting were the same for each trial. However, it was also accurate. It was also an accurate experiment. As a it also used appropriate equipment and setup due to using a very accurate measuring tape. 2 decimal places. So how can we improve the accuracy, right? How can we improve the accuracy? Well, again, we can use better equipment. So accuracy can be improved such as replacing the Nerf gun with maybe with a specialized ramp, right? So maybe something like a ramp where you roll it down up again. So for example, it might look like look like this. You might roll it down and up again. And that's just a little bit more. It's easier to position, makes it you can also replace the measuring tape with a camera, right? So the camera can record the entire motion and deduce the range, period accuracy, because sometimes it might bounce and roll and you measure the wrong distance. Also upgrading. Also, the ball/bullet itself could have a range sensor, which would make it more accurate. A range sensor that'll make it more accurate. Or you could use digital equipment. Upgrading the protractor to have more decimal places and to be digital. Same for the ruler. How can we improve the reliability? Well, that's pretty simple. So improve reliability by repeating the experiment. By repeating the experiment 10 more times, right? 10 more times. It doesn't matter how many times you say, because you're not doing it, right? And average the results. Oh yeah, sorry. The other thing, the one thing I was going to say here is that also, you can see that there's a lot of outliers. Also, there are quite a few outliers indicating the experiment is not reliable. So yeah, as I was saying here, right? To average the results, remove the outliers that you get and the current outliers. And finally, test over a larger range. And sorry, not necessarily a larger range, but test over more values. So for example, instead of going 5, 10, 15, you can go 2.5, 5, 7.5, 10, 12.5, etc. And that gives you more resolution. This gives more. This gives because you can see that because of the nature of sine, you can see that we don't really have that many values towards the small parts. They all get clustered towards the end. Sorry. I just realized when I saw that we haven't really. There are some things that we can add to the assessment of reliability, actually. So this can be seen on the. On the graph, where there are points towards the right that do not obey the trend line. So these points probably need to be like this one, this one, this one probably need to be examined in closer detail, right? So this is indicating that the reliability has been reduced. Improve the validity. We can improve the validity by again improving the equipment, improving the equipment used. So we can probably just copy paste this from accuracy. So like again, using a ramp, using a camera instead, using a bullet with a sensor, upgrading the protractor to be digital. You also so for example, another variable that you could control for is so like for example, like one thing is that the air resistance. So control for different air resistances. Because something that is true is that air resistance actually scales quadratically with your speed. So this means that these bullets don't actually will have the same air resistance. So it's actually not going to obey that formula directly. So what you can do by doing the experiment in a vacuum, right? In a vacuum. You should probably also control the way that the bullet is fired. So you want to make sure that the same operator is there, and make sure that the hand is not shaky. So one way to control this, so it can be controlled by using a stand and a string to pull the bullet, to pull the trigger. Yeah, I think that's about all that we need to do for this exam. I hope you guys enjoyed. Thanks for watching till the end. If you want more, please just check out our website, and if you enroll, we have plenty of other sample exam preparation materials just like this. So I will see you guys soon. Bye bye.